Green's Theorem, Part 2. In Part 1, we focused on the circulation form of Green's theorem. Circulation adds up the components of a vector field in the direction of a curve. In Part 2, I'd like to focus on the flux form of Green's theorem. Flux adds up the components of a vector field that are orthogonal or normal to a curve. Alright, so let's assume we have a curve that is a simple, closed, smooth curve, oriented counterclockwise with outward normal vector n. Let's assume that the curve encloses a connected and simply connected region that we will call R. Now suppose our vector field, let's suppose that its components have continuous first partial derivatives. As I said, flux adds up the components of f in the direction of the normal vector for each point on the curve. Now the flux form of Green's theorem relates the flux across C to a property of the vector field within the region that produces the flux. F partial x plus g partial y is called two-dimensional divergence. Let's just talk about divergence for a minute. Suppose we're at a point P. If f partial x is positive, that would indicate an expansion of the field in the x direction. If g partial y is negative, that would indicate a contraction of the field in the y direction. Well, what about the sum? Let's suppose that the sum f partial x plus g partial y, let's suppose that the sum is negative. That would indicate a net inward flux across a small circle enclosing P. So two-dimensional divergence, if it's positive, that means an expansion. Negative means a contraction. Now what if it's zero? What if two-dimensional divergence is zero? A vector field that has two-dimensional divergence 0 at every point is said to be source-free. And an example of a source-free vector field is the rotation vector field. Another example of a source-free vector field that we haven't seen yet is this guy. Its x component is sine y, and or I should say its f component is sine y, and its g component is sine x. So f partial x plus g partial y is always 0, meaning that it's source-free. Now let's use Green's theorem to compute the outward flux of this radial field across the unit circle. The radial field has two-dimensional divergence. The curve is the boundary of the unit circle, so the region is just x squared plus y squared is less than or equal to 1. And this region has an area of pi. So the outward flux of the radial field across the unit circle is just going to be the double integral of 2 over our region, which is just a circle of radius 1, or the interior of a circle of radius 1. So the outward flux is 2 pi. And this is the calculation we got using line integrals. The positive divergence on our region is consistent with an outward flux of the vector field across the boundary of our region. Let's evaluate this line integral where C is the boundary of the disk of radius 2 centered at the origin. And let's assume that C is oriented counterclockwise. Notice that if we choose the vector field in this manner, so we're choosing this vector field, then the line integral is a measure of the flux across the curve that contains our region. So we can use the flux form of Green's theorem to turn the line integral into a double integral over the region bounded by our curve. So let's find two-dimensional divergence. We need to find f partial x plus g partial y, and then evaluate two-dimensional divergence over our region. So f partial x, g partial y, find that, and then find the divergence, find the sum of the two. Okay, so we found divergence, and so Green's theorem tells us that all we need to do is find this double integral. Now, what's our region? Let's remind ourselves of that. Our region is a circle of radius 2. And so the easiest way to evaluate this double integral is using polar coordinates. So get out your polar coordinates thinking cap. With polar coordinates, x squared plus y squared equals r squared. And our region can be described with r going between 0 and 2 and theta going between 0 and 2 pi. Now don't forget that extra factor of r when you switch over to polar coordinates. And so I just evaluate it and I get 96 pi. Let's find the circulation. So now we're switching over to circulation. On the boundary C, where our region is a half annulus. The curve runs in the counterclockwise direction on the outer semicircle and clockwise on the inner semicircle. And the orientation is the orientation shown in the illustration. Since the curve runs counterclockwise on the outer semicircle, the field is roughly opposed to the direction of the curve for that section of the curve. For the inner semicircle, the curve runs clockwise, and the field is approximately aligned with the direction of the curve. Lastly, along the x-axis, the field is orthogonal to the direction of the curve, telling us that the dot product is 0. Since it appears that the dot product is negative longer than it's positive, we would expect the greater contribution to the circulation to be negative. All right, so using Green's theorem, the curl, we're doing circulation, so we're looking for curl. The curl is 2x minus 2y. Now, if we switch to polar coordinates and evaluate, we get negative 104 divided by 3, which is what we were expecting, an overall negative circulation. Take care, and I'll see you in part 3.